Hello and welcome to all students. In this lecture, we learn about the unit number 3, inner product spaces. So, in this chapter, first of all, we see the introductory part, then we see the inner product on a real vector spaces, then distance and norm of a vector, and finally, we see the orthogonal and orthonormal sets. Okay, so first of all, we have some introductory part, introduction. We are familiar with the notation of dot product of two vectors in a plane R2 or in a space R3. We are also familiar with the properties of vector spaces. Vector spaces are also known to you. We can define the concept of magnitude, distance and angle in plane or in space in terms of dot product. In this chapter, we shall generalize the concept of dot product to an arbitrary vector space. Now let us define the inner product on a real vector space. So let us start to define the real vector space or definition of inner product. First of all, we define what is inner product. Inner product. An inner product on a real vector space V is a mapping which assigns a real number denoted by UV to every pair of vectors. Okay. So first of all, we see the inner product is a mapping. So let us write an inner product is a mapping an inner product is a mapping an inner product on a real vector space V. Inner product on real vector space V. An inner product on a real vector space V is a mapping which assigns a real number which assigns a real number denoted by this notation u comma v to every pair of vectors u and v to every pair of vectors u and v in in V is a vector space such that the following properties are satisfied for all vectors u and v. Okay, such that the following exams AXIOMS, the following exams are satisfied by all vectors u, v, w in V. And what are these properties? So let us write these properties one by one. So first property is inner product of u with v is equal to inner product of v with u, and this property is known as symmetric property. This property is known as symmetric property. Okay, now let us write the second property. Inner product of u plus v with w is equal to inner product of u with w plus inner product of v with w. This property is called as additive property. Additive property. Now next third property is inner product of k into u with v is equal to k times inner product of u with v. Okay, scalar multiplicativity. Okay, next fourth property is inner product of u with u is greater or equal 0. This property is called as positivity. And inner product of u with u is equal to 0 if and only if u is equal to 0. A vector space with an inner product defined on it is called as inner product space. Okay, so these are the four properties which are satisfied by inner product. A vector space with an inner product defined on it with an inner product defined on it with an inner product defined on it is called inner product space. Is called inner product space. Okay, so let us take one example on the inner product space. Okay, so let us write one example on inner product space. Consider a vector space Rn. Consider a vector space Rn and let U equal to a vector u1 comma u2 comma dot 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 up to un with n components. Vector v is equal to v1 comma v2 comma dot 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 comma vn, vector with n components, and vector w is equal to w1 comma w2 comma dot 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 up to wn. So consider these three vectors in Rn. Okay, and let k belongs to R be any scalar okay. Now let us try to prove all these four properties and show that. Okay, so consider first now. Consider this notation: inner product u with v is equal to okay. How first of all we define okay. Then inner product of uv is equal to uv na inner product of uv equal to u1 v1 plus u2 v2 plus dot 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 plus un vn defines an inner product on Rn. Defines an inner product on Rn. Okay, we have to show this notation defined like this is an inner product on vector space Rn. Okay, so for that we have to show that this notation satisfies four properties as stated in the definition. So let us try for first property. Consider this notation: product with uv is equal to, by definition it is u1 v1 plus u2 v2 plus u3 v3, and it is equal to, as ui's and vi's they are real number and the product of real numbers is commutative, therefore we can write it is v1 u1 plus v2 u2 v2 u2 plus dot 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 plus vn un. So there must be n here, okay, and here must be like this, plus dot 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 plus un vn. कुठली मी ठेवली हवा यायला जरा. Okay, and so by definition this is nothing but inner product of v with u. Okay. So first property is satisfied by this product. Now let us go to the second property. Second property says that inner product of, okay, so consider this notation: inner product of u plus v with w. Okay, and it is equal to, we know that what is u plus w, it is u1 plus v1, u plus v1, u plus v, okay, into w1 plus u2 plus v2 into w2 plus dot dot plus un plus vn into wn into wn. It is equal to, so multiply inside, you will get u1 w1 plus v1 w1 plus u2 w2 plus v2 w2 plus dot dot plus un wn plus vn wn. करा काय पण चपाती भाजी करा, मेथीची भाजी चपाती. So consider these terms. Okay, so these terms are nothing but the inner product of u with w, and remaining terms are nothing but the inner product of v with w. So this second property is also satisfied by this product. Okay, now let us go to the third property. Third property says that, okay, so let us consider inner product of u with itself. So by definition it will be u1 square plus u2 square plus dot 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 plus un square, and we know that ui, if ui is a real number, then ui square is always greater or equal 0. Therefore, the summation of ui square, okay, I runs from 1 to n, this summation is also greater or equal 0, and therefore the inner product u with u is greater or equal 0. So this is non-negativity or positivity, that property is satisfied. And finally we will show that consider now if we have inner product of inner product of u with u, inner product of u with u is equal to 0. This is equal to 0. So this is if and only if and only if this is equal to 0, u1 square plus u2 square plus dot 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 plus un square is equal to 0, and this addition is 0 if and only if ui square is equal to 0 for all I equal to 1 to up to n. Okay, so and this ui square is 0 means ui is equal to 0 for all I equal to 1 up to n. Okay, so all ui's are 0 up to 1 to n means the vector u is equal to 0. Okay, so we have this thing, inner product u with u equal to 0 if and only if vector u is 0. So all four properties are satisfied by this product, therefore it is a inner product on Rn. Therefore product u with v defined above is an inner product on Rn. Okay, so this is the way to show that some definition of product, inner product is an inner product on Rn. Okay, so let us go to the next. Let us take one example now. Let us take next example. Example number 2. Example 2. On R2, let us define on R2 define for u equal to x1 comma y1 and vector v is equal to x2 comma y2. So define the product uv is equal to only product of first component x1 x2. So find whether it defined an inner product on R2. So question is an inner product on R2 question mark. Whether it is an inner product on R2. So let us check now. How to check? So we write the answer. So how to check whether it is an inner product on R2? So check these four conditions defined above in the definition, whether all these four conditions are satisfied or not. Okay, so we observe that here product is defined like this. So we are taking here in product of two vectors is nothing but the product of first component of both the vectors. Okay, so if I take a vector u is equal to suppose 0, 1 and vector v is equal to, okay, so only one vector is here. If I take vector u is equal to this and look at the product u with u, now product u with u is nothing but 0 into 0 and it is equal to 0. Okay, so product is 0, but the vector u is not equal to 0, and this is the violation of which condition? This is the violation of this fourth condition. Okay, so fourth condition is not true, therefore the defined product u with v is not inner product on R2. Okay, it is not an inner product on R2. There are many examples. Okay, so today we stop here. This is the end of our lecture. Thank you.